Okay, folks, as always, announcements to get started. There's homework one that's on Canvas. It's due in 1 week. That's next Tuesday. You have 7 more days. And if you haven't started already, please start soon. Some of you already started. And, this is the homework where you get used to all sorts of logistical things, like figuring out how Gradescope works if you've never done that, or just getting your environment set up. And these things take longer than they need to. Always they take longer than they need to. So it's better if you start soon and just get those issues out of the way. I saw that there's some discussion on Piazza already. Keep that going, keep that up. And if there are questions and such things, don't feel shy about asking. Also take advantage of office hours. There was one office hours this morning. Tomorrow there'll be one, and on Thursday I'll have my office hours. So you'll have a few occasions to clarify your questions before the homework is due. So make sure you take advantage of that. Are there any questions about the homework? Have people started? Some people. You have a question? No. Oh, you just started. Okay. A few useful things to keep in mind. If you do the theory part of the homework by hand, you'll get a sense of how this algorithm works, and that's going to make your implementation more, it'll kind of help you figure out your implementation quicker. So do that first. Also, you can use the data set from the theory part of the homework for debugging your decision tree code. Another thing to note is cross-validation, which you're supposed to run. We haven't covered cross-validation formally in the class. I'm using the homework as a mechanism for you to introduce concepts that are important, that you'll have to do in experimental machine learning every single time you do it. We'll talk about cross-validation sometime in the middle of the semester, but I wanted to kind of get you going with that early on. Cross-validation can take some time. So make sure that you allocate sufficient time to run and debug your code. Okay. Any last minute questions? Another announcement is, did you have a question, Iris? Okay. Another announcement is, I mentioned this last week. We have the Utah Data Science and AI Day. This is happening on Friday. There is a career expo. There's some networking lunch where you get to meet people with similar sorts of interests. There are research talks by faculty from around campus. And there is an invited keynote speaker, Dieter Fox, who's a very famous roboticist, who's going to talk about the question of RoboGPT. And it promises to be an all-around interesting event. There are details on this website, datascience.utah.edu. Feel free to register. I think there's also breakfast, there's also breakfast. If you have any questions about it, figure it out on the website. Don't ask me. Any other logistical things you want to discuss before we dive back into technical things? No. Okay. So let's jump back into where we were. In the last lecture, we were wrapping up our discussion of decision trees. We had already seen this question of what decision trees are, and we saw this ID3 heuristic for learning decision trees. And we were looking at some extensions. In particular, we looked at some variants of the ID3 heuristic. The ID3 heuristic, remember, is based on this notion of information gain. Information gain is based on the notion of entropy. Entropy is supposed to characterize the disorder or impurity or uncertainty in a data set. It turns out there are other ways to characterize disorder, impurity, uncertainty, other than entropy. So using those other definitions, you can create other versions of information gain. And in your homework, we ask you to do that. There are a few different variants, and we saw majority error and Gini index. I think in your homework, we ask you to play with Gini index. And for grad students, we ask you to implement a completely different measure of an information gain, invent an information gain using a completely different measure of uncertainty called collision entropy. And then we also looked at some heuristics on how to handle missing features. Basically, the idea there is sometimes when you're taking measurements from your data, maybe the device that's doing the measurements fails. And so you may have data sets where some features are missing. And the high level intuition for this problem of missing feature imputation or missing feature reconstruction is to use the neighboring data, use the data, the signal that you have about other features and the label on that for that observation to reconstruct that feature so that you get completed data. We looked at not twice, we've looked at how to handle non-Boolean features. In particular, if you have numeric features, you basically bucket them. You threshold them and create categories so that you can create a decision tree. The thing that's left here is this discussion of overfitting. And that's where we're going to start today. But before that, any questions about any of these things? Now that you've also seen, hopefully started looking at these ideas in your homework. Yes. Sorry, can you say that?
We need to share that information.
Yes. Yes. Yeah. Yes. Yes, that's right. That's right. So just to repeat that in case you didn't hear that, we use Shannon information in the, or Quinlan used Shannon information in the original definition of ID3, but there are other definitions of information. Other questions, comments? I see you're all eager to get into overfitting. So let's just do that. To introduce this idea of overfitting, I want to reintroduce you to this function that I mentioned at the end of the last lecture called the first bit function. The first bit function is a decidedly degenerate function. Imagine that you have a feature vector with n features, all Boolean. In this case, you have two of them, x0 and x1. And what the function does is no matter how many features you have, it takes the value of the first feature, x0, and copies it over to the output. So the function is simply y equals x0. x1 in this table is irrelevant. And if you have n features, everything from x1 to xn minus 1 are irrelevant. Obviously, this data can be captured by a decision tree. Well, a decision tree can capture any Boolean function. You can definitely do this. In particular, for this Boolean function, no matter how many features you have, the decision tree looks exactly like this. It copying the first feature, it looks at the value of the first feature, x0, and if x0 is true, the label is true. If x0 is false, the label is false. And another sort of a unit test for your ID3 implementation could be give this data to your implementation. It should produce exactly that tree. If it does not, suggest that there's a bug. Right? Okay, now let's consider the case where we have a function of this sort, and you have the entire truth table. If you have n features, your truth table will have 2 power n rows. Right? So there are n Boolean features. Every feature can be a true or a false, 0 or a 1. It can take two values. There are n such things that can take two values. So there are 2 power n possible assignments to these features. Your instance space has 2 power n entries. Now, let's say that your learner gets access to every one of these examples. Will there be any error on future examples? And let's say you train a decision tree. Will your decision tree make errors on future examples if your learner has all the data? You're nodding no, why not? It has every possibility that it can hit, and your decision tree will fit the data perfectly. Your decision tree will catch every single row of the table, which means your decision tree will be a perfect summary of the table. Any future example, I talk about future examples here, but any future example has to be one of these 2 power n rows. It's already seen that row, and it's memorized it. So since your decision tree can represent the function and build a tree that is consistent, I'll use this word multiple times through the semester, your ID3 will build a tree that is consistent with the data. There are going to be no errors on future examples because there are no unseen future examples. Every example has been seen. Okay. Let's now make this a little bit more messy. Let's say that the labels are corrupted randomly. So let's say that you have all 2 power n rows. In this case, you have 3 features, you have all 8 rows, and some labels are changed by an adversary. Well, not an adversary, by some noise. It could be measurement noise. So you have a table during training that may look something like this, right? Okay. Now, the same question. What about your training error? Yes. Will your training, no, on the training data, tell me what you, so let's first define the terms here. Training error is the error of the tree that you learn on the data that was used to train it. So can you tell me what's the training error of a tree that's trained on this data?
0.
Why?
Because it has access to all this information, it's memorizing the outputs, and so it'll always get it right.
That's right. The decision tree learner is a consistent learner. It will create a tree that's consistent with the data. Just so happens that the data has noise, but at no point in your ID3 algorithm did you ever consider, is this example noisy? It doesn't care about that. It's just going to memorize the noise. Okay. What about the test error? Future examples. Will the test error, will the learner have errors on future examples? You're nodding yes. Do you want to say why? Okay, there are 2 of you who nodded yes, but I didn't catch you, but go ahead. That's right. If the second row shows up, this time accidentally, the label did not get corrupted. The learner is going to predict true for that row, when actually the actual label was false, because remember the original function is going to copy over the first bit. Similarly, if maybe some other row, let's say this row showed up, and accidentally the noise process corrupted the label for that one, the future example will have a label false, whereas the tree is going to say true. So there are 2 kinds of mistakes it can make. So that means even though the training error is 0, future examples may still encounter the learner will still make mistakes on future examples. At some point, I did a quick simulation here with test accuracies for different number of features, and at no point do you get 0 test accuracy. This is accuracy, not error. The height of the bar is the fraction of future examples that the tree gets correctly, and I repeated this multiple times. And just as a interesting sort of a side note, it turns out that the error converges to 0.375 if your corruption rate is 0.25. And there's an explanation here. You can see this offline. I don't want to spend time on this. You can derive this very easily. But of course, the training accuracy, even though the test accuracy is not 100%, the training accuracy is going to be 100%. And we've talked about that. The training accuracy is 100% because the learning algorithm will find a tree that perfectly fits all the data, including the signal and the noise. And that's the important point here. So any questions about this? This is a situation. This situation is an example of overfitting. Your learning algorithm finds a hypothesis that fits the noise in the data because data does not come tagged with this example is noisy and this example is not. Your learning algorithm, because the ID3 algorithm essentially seeks to represent the entire data that you have, essentially memorize the data, the number of the not the number, but the noise in the data will influence the learning algorithm to produce possibly an incorrect tree. It could be irrelevant features that seem to be accidentally correlated with the label, or noise in the features, or noise in the data. Because your learning algorithm found a hypothesis that looks that memorizes the noise in the data, it can lead to poor performance on future examples because the noise in the training data has made the learner find a tree that's not going to give the right label for future examples. This situation is called overfitting. We will be talking about overfitting quite a bit. Overfitting is the key problem that machine learning has to address. I'll give you one definition of overfitting today. Sometime in the middle of the semester, we'll look at other definitions also. They're not incongruent definitions, they're just different ways of looking at the same idea. Imagine that your data comes from some probability distribution. There's some process in nature that generates your data. And I'm calling that distribution capital D. It's quite likely that we do not know what that distribution is. The process in nature that creates cats and makes them look fuzzy and such things and makes them photogenic is a random process. We do not have a formal probabilistic characterization of the process that generates photographs of cats. So, but there must be some distribution. It might be a very complicated distribution. We don't care what it is. Let's just give it a name so that we can talk about it. That distribution, I'm calling it D. And we have a hypothesis space, capital H. Capital H is this set of functions that your learner is going to explore to find a hypothesis. That hypothesis, I'm going to call it little h. There are two kinds of errors that are of interest. There's something called the training error. The training error is simply the error of the hypothesis on the training data. The fraction of training examples that your hypothesis mispredicts on. The training error is something you can measure. Given a hypothesis, you can always essentially ask the hypothesis for the label on the entire training data, and then count how many times you got it wrong and divide by the number of examples. That's your training error. And then there's something called the true error, the thing that we actually care about. The true error, sometimes also called the generalization error, the generalization error or the true error is the error of the hypothesis, is the expected error of the hypothesis on a randomly sampled example produced by this distribution. The same process that generated the training data, if it gave you one more example that was not seen before, what's the probability that your hypothesis makes an error on that example? Notice that the true error or the generalization error is not something we can actually measure because we do not have access to the true distribution. We can only get samples from the true distribution. I can get you photographs of cats, but I can't actually tell you what the distribution is that produces photographs of cats. On a random sample, I can ask, is the hypothesis going to make a correct prediction or not? But what I really want to measure is the probability of making the correct prediction or the probability of making an error. That's the generalization error. Questions about the true error and the generalization error? Yes.
So just to clarify, training error is something we can measure because we have access to the training data, whereas true error, generalization error, we can't directly measure it because we don't have access to the distribution.
That's right.
Got it.
We do not have access to the distribution. But it's a concept that we can talk about, right? It's an idea that we can talk about. Using that idea, we can define generalization. Sorry, we can define overfitting. We say that a hypothesis little h overfits the training data if there is another competing hypothesis. Let's give it a name. Let's call it h prime. So there are two hypotheses, h and h prime. And we say that h overfits the training data if the hypothesis h has a lower training error than the competing hypothesis h prime. So the training data makes it look like h is better than h prime. But in fact, h has a higher generalization error. In other words, h prime generalizes better on future examples. To make this more, to just write this in symbols, the training error is nothing but error subtrain of h is less than error subtrain of h prime. But error d of h is greater than error d of h prime. The true error is, according to the true error, h prime is better, but the data set confused the learner and made it pick h, which is worse, because h looks better on this data set. So your learning algorithm has decided, maybe we've not yet talked about our learning algorithm, we're just talking about hypothesis. The hypothesis h is said to overfit the hypothesis h prime. And one of the goals of designing learning algorithms and practically implementing them and using them is to invent learning algorithms and all the design choices that go with it, such that the learning algorithm never prefers a hypothesis like little h. Questions? Also on Zoom, if there are any.
Sorry, I have a question. So, if we said that the errors can't really be measured, how can we make the comparison between H and H prime?
Clarity. So you said probably we have distribution of capital, right?
Yes.
Not go for this. I'm thinking about that.
I didn't understand your confusion, but I think I know the answer to your question. The thing is, all we have to kind of understand about the concept that we are learning is the training data. We do not have access to the true distribution. The learning algorithm somehow has to figure out that, has to somehow bias its behavior so that it does not accidentally find explanations of the data that are surprisingly too good. Because if it is, then there's a good chance that it has ended up overfitting. Because we do not have, what we would like is to find a hypothesis, given if the only two choices you had were h and h prime, you would prefer that your learning algorithm picks h prime. But the learning algorithm has no information other than, no information about the true concept other than what it sees in the training data. So there must be some choices in the design of the learning algorithm that are not purely data driven, so that it avoids gravitating towards x. These are, sometimes we call them hyperparameters. These are choices that govern how the learning algorithm works. And in order to do that, what we would prefer to do is we want our learning algorithm to find hypotheses that maybe make more errors on the training data than something else, with the hope that it will generalize better. I say hope now. We will say, we'll see mathematically more rigorous versions of that hope later. There's a question on Zoom. Can the true, oh, yes. Just wondering if oh yeah, this is it's a related question. If the true errors cannot be measured, how could we possibly compare the errors between H and H prime? This second row here, point number 2 here, is something that cannot be measured. So how could we possibly say that? For now, I want you to treat this as just a conceptual idea. I can always talk about that probability, even if I can't measure it. But there is a way to kind of estimate that probability. Can someone give me some ideas on how I can estimate the error on future examples? Yes? So the suggestion is you get a separate set of examples. That's what we do in practice. That's what we always do in practice. We have a set of examples that the training algorithm did not have access to. These examples are called test examples. And we measure the error of the hypothesis on the test data. It's the average number of mistakes it makes on the test data, or the fraction of test examples it mispredicts. And if the test set is large enough, by the law of large numbers, we get a increasingly better estimate of the generalization error. So this is also a point about machine learning practice. If you have a data set, one of the first things we always do is we partition it for a new task. We partition it into a training set and a test set. The training set is what your learning algorithm uses. The test set is how you evaluate what the learning algorithm produces. If you ever use the test set as part of the training data, your learning algorithm will also overfit the test data, which means you no longer can measure generalization error. So that's also the answer to the question on Zoom. How do we compare the errors? We use a test set in practice. And we also assume and try to design things so that the test set is a good representative of the true distribution. That's a good segue into this next plot. Decision trees. Wow, that picture is terrible. It's slightly less terrible on my screen, but okay, I need to fix this. Decision trees will overfit your data. Here's a plot from Tom Mitchell's textbook, where the vertical axis is accuracy and the horizontal axis is the size of the tree, which is just the number of nodes. And as your decision tree grows, as the decision tree gets bigger and bigger, it seems like the training error goes down. The tree starts fitting the data better and better. However, after a certain point, the generalization error or the test error starts going down. And the test error here is measured on a held out set of test examples. So this means a good way to avoid overfitting is to maybe stop growing the tree somewhere here. Even though after that point, it seems like you can still get a few points of gain on the training data, you actually lose on future examples. So in this data, maybe a good place to stop is after about 20 nodes, you don't grow the tree anymore. So how do we avoid overfitting? So decision trees, this is an important point. Decision trees will overfit your data if you do not explicitly do something about it, because your decision tree learner is a consistent learner. It will memorize not just the signal, but also the noise in the data. That means you do not really want to have it memorize everything. You want to stop growing the tree at some point. And in your homework, we ask you to consider depth limitation. After a certain depth, you stop growing the tree and use cross-validation to evaluate this approximation of test error. So here are some ideas to avoid overfitting with decision trees. All of them go back to this idea of Occam's razor. We'll spend a lot of time talking about Occam's razor later on. But the basic idea is that if you have two hypotheses that are similar in their ability to explain data, pick a hypothesis that is simpler. In this case, simpler means smaller tree, because smaller trees are less likely to explain a data set just by accident. So if you have a small tree that gets 85% accuracy and a massive tree that gets 86% accuracy, sure, the massive tree seems more accurate on the training data, but the smaller tree could not have explained the data up to get 85% just by sheer coincidence. So that must be the signal. That's the intuition here. An extreme version of this intuition is to fix the depth of the tree to just one level. So you find a feature, one feature, and then immediately predict the label. Such a thing is called a decision stump. By themselves, decision stumps are not good. But it turns out decision stumps become useful when we want to have a second degree of another classifier that sits on top of them. We'll come to that somewhere when we talk about ensembles. But another version of this idea is you just fix the depth of the tree, not to 1, but some depth, 5, 15, or something, so that your tree does not grow arbitrarily large. Of course, you need to know how to fix the depth of the tree. The depth of the tree is something called a hyperparameter. It's not actually controlling, it's not something that your learner produces, but it's a design choice that you feed into the learning algorithm that controls the hypothesis returned by the learner. So this hyperparameter choice, it turns out the way to pick a hyperparameter is a bit of an art in machine learning. One way of doing that is to use something called cross-validation, which you're doing in your homework. We can talk about that a little later. Another thing to do is you optimize the decision tree learner on something called a held out set. This is what I mentioned before. Sometimes it's called a development set or a validation set. So you have your training data and your test data. Your test data is for future evaluation. We cannot choose hyperparameters based on the test data because then it will memorize the test data. So then you have, let me write this down. So this is your full data set. This block here is all the examples that exist. I have split this into 2. This part is train, and this part is test. And now you're not allowed to use this data at all, because that part is going to be for evaluating your tree, the one tree that your learner will produce. So now the goal is to use your training data to somehow construct a good tree, also find a good depth. So what you can do is further partition your data, the training data, into 2 parts. This I'm going to call the train, and this is the development set or the validation set. You grow your tree on the training data up to a certain depth, and then you evaluate that depth on the examples on the dev set. The dev set behaves like future examples, and you try that for different depths and pick the one that is the best. Or you can keep growing the tree till the performance on the dev set goes down, or something like that. Are there any questions? I'm kind of mixing something called model selection with the hyperparameter, with the depth limitation idea. But are there questions about either one of these things? Have people seen hyperparameter selection before? One person. Okay. So this is something that you will be doing a lot of in every instance of applied machine learning. Most of your computational effort is going to be spent on hyperparameter selection. Every single new learner that we encounter, every single new hypothesis class we encounter will come with its own hyperparameters. And when we talk about machine learning being computationally expensive, a large part of that compute goes towards choosing good hyperparameters. Yes.
I guess, would we want 3, split our data set into 3 sets, training, testing, and like a held out set, right?
Training, test, and dev. Yeah, basically 3.
So we want 3.
Yeah. So because I've already split the the data into train and test, and then I'm further splitting the train into 2 subparts.
Yeah.
Yeah. Or you could split it into 3 and make it easier. Yeah. It's the same thing. Yes.
Just to clarify, you would essentially kind of do like a kind of a test with every time a new node is added within the dev set to see if it's time to stop growing.
Something like that. You could do that, or you could just decide that you're going to consider these different depths, and only at those points you're going to measure the tree that is generated.
So it's kind of like
It is exactly a hyperparameter. Yes.
So we can consider the held out set as sort of like a pre-test of sorts.
Like an
during the training.
like an internal test. Yes. It's an internal test that you use to decide these operating characteristics of your learning algorithm. There's another thing, another idea that also works for decision trees, which is you grow your tree to full depth, fitting both the signal and the noise. And then after you grow the tree, you start pruning branches. The tree metaphor works fantastically here. You start essentially pruning the leaves and making the tree smaller and smaller. And every time you make a snip, every time you cut, you measure the performance on the validation set and pick the one that gives the best accuracy. A slight variant of that is, it turns out, in practice, you can also convert your decision tree into a set of rules. I briefly hinted this last week. You can convert your decision tree into a set of rules and prune rules also. It's an idea that is practically useful, but it's a little bit engineering heavy. So I'm not going to spend much time on this right now. So let me wrap up this part on decision trees. Decision trees are a useful tool to have in your machine learning toolkit. Prediction with decision trees is easy because it's basically following the tree down to the leaf. Training requires essentially considering the entire batch of examples and getting statistics from that to decide how to split and recursively doing that. If you have non-Boolean features or non-categorical features, you need to do a little bit of extra work before the data becomes in a format that can be used by the learner. There are many robust implementations of this of variants of ID3, in particular something called C4.5 or C5 that exists. You can use decision trees for regression also. We only looked at decision trees for classification. You can use it for regression, and the way it works is, in classification, the leaf of the tree is a label, right? In regression, the leaf of the tree becomes a function that produces a number. One of the more important things to worry about with decision trees is they are quite likely to overfit your data unless you do something about it. And what that thing is usually involves restricting the size of the tree, either by not growing it and limiting the depth, or by growing it all the way down and then pruning it back. One way or another, you need to restrict the size of the tree. Decision trees are not, you don't hear about decision trees on the front page of New York Times. They don't seem that fancy, but they are a very useful tool to have, because among the machine learning technologies that exist out there, this might be the one that is most interpretable. The actual chain of decisions that led to the label is explicitly there in the decision tree. Every other classifier that we encounter does not have the property. So decision tree is useful also as an interpretability device, if you want to go that way. Any questions?
Please use the real-world scenarios in a commercial setting. Or should we more likely to use more complicated?
It depends on what the situation is. As recently as a few years ago, I mean, I'm talking maybe, I say a few years ago, about 5 years ago, a student of mine who was doing an internship told me that in some e-commerce company, basically a lot of things they do are glorified decision trees. But with tools like generative AI, you don't see decision trees. But for interpretable decisions, they are useful. And another place where decision trees become incredibly useful is when you have not one tree, but you grow a committee of trees, and then you start aggregating their decisions to produce a final label. That is an extremely robust predictor. So that tends to be used more than other places. As recently as a few years ago, I would say maybe 2 or 3 years ago, I remember Cynthia Rudin from Duke was talking about how decision trees are the best thing to use if your data is not um, text or images or such things, but more like measurements from of socioeconomic factors, for example, of multivariate, very diverse kinds of measurements that you want to aggregate together into a predictor. She's done some fantastic work on those sorts of problems using decision trees. So they do get used, especially when you want to produce a model whose decisions need to be audited.